Good morning. Very warm welcome to ISIN 24. My name is Kotuchko and I'm one of the tutorial co-chairs organizing here the tutorials. I wish you, I'm very happy that you're here. We have quite a decent audience. Thanks a lot. Also, I hope that we have an interesting tutorial program. We have 2 tutorials today and 2 tomorrow, so I'm looking forward to this. Yeah, I don't want to say too much. I think there are the tutorials presenters are already eager to give the tutorials, and we have also some students here who are helping us with the organization of the tutorials, and I think this is very important to engage, especially as young students here with industry. And that was one of our aims also of these tutorials, and so I'm very happy to have a tutorial here from Orange with the industry part on a very new topic on these pipelines. I'm personally a little bit interested in these pipelines because I did a lot of more, and maybe this is surprising, software engineering for AI pipelines lately in an EU project. So that's a little bit my personal interest. So I had like to hand over to the students who give the full introduction. So I think that's even better than I'm doing this. Thanks a lot, please.
Good morning, everyone. Well, today we are going to start with the tutorial setting up a reinforcement learning pipeline for a Telco core network. Our first speaker is going to be Jan Fraisse. He first got a software engineering master degree in 1999 in the University of Bordeaux and worked as an engineering and architect in different capacities at Orange while getting his master's and his PhD in Sorbonne University. He has since been managing the cognitive and predictive network management research project at Orange. One of the focus of this project is exactly the automation of the management of core networks using reinforcement learning. Our second speaker is Shantanu Verma. He holds a bachelor's degree in computer sciences, and he started his professional career with Orange in 2020. He has worked as an engineer on multiple AI projects, with use cases focused on telco and cloud, being associated with cognitive and predictive network management research project at Orange from 2021. He has contributed on engineering and designing the different aspects of problems of resource scaling of network functions using reinforcement learning. So, well, I will pass the micro to the speakers.
So thank you, Gabriel, and hello, everyone. So we are going to be together, I hope, for 2 times 1 hour and 30 minutes for this tutorial. So I'm going to start speaking about that. So this tutorial, as it's written and introduced, is about using reinforcement learning pipeline for a telco core network. So that's a lot of things to cover, a lot of different skills. So this first part will be about introducing the different aspects, a technical aspect, so both on reinforcement learning, but also on the telco core use case. So you can hopefully follow the second part, which would be more hands-on, where we have provided already a GitHub link, and also we will go through that also a little bit in the first part to make sure that you can follow the hands-on part after that. We know it's going to be a bit difficult to have everyone who wants to follow the hands-on part because there's so many use cases of what kind of environment you have on your laptops and so on. So there's also the possibility to run everything in a Google Colab and with nothing to install on your laptops, and it should be easier. But hopefully you're going to be able to also follow later the hands-on part. This work is like a sum up of the last 3 years, let's say, of a project where we worked on exploring how to use reinforcement learning for telco core networks. So what we're presenting today is not only the work of Shantanu and me, who are here, but also from other members. So I'd like to acknowledge the contribution of Abhishek and Jatinder, who are also, like Shantanu, from our team in India. Gabriel, who just did the introduction and the new intern in the project. And also past members, so even if we have one here. So we have Manu Chauhan, who was Orange India and now at Tavent, Francesca Fossati, who did a postdoc here and is now an associate professor at Sorbonne University. Imen Grida, who actually started this project and who will be here on Wednesday to give a keynote and now works at Amazon Web Services. Also, we had Chin Chilong as a master's student last year who's now finishing her studies in Beijing. And also we had the visiting researcher Yoichi Matsuo from NTT Labs in 2022. And all this work led to, so far, a couple of publications that we presented last year during the NOMS conferences. So a lot of what we are going to present here was actually the tools we set up and feedback and lessons learned from what we've done for these papers and the current work we are doing. So we took a little bit of assumptions about attendees today. So we consider that you have more network background, so maybe you have limited knowledge on reinforcement learning and machine learning in general. So maybe a quick survey of the room. Does any one of you have already experience in machine learning and reinforcement learning? Or is it, yeah? And is it a brand new topic for the others? Yeah, mostly? Okay, so we're gonna start from the ground up, hopefully introducing everything you need to understand to follow today. So machine learning, let's start from the ground up. So machine learning, best definition probably I could find. We use this term when a computer program is said to learn from an experience E with respect to some class of task T and performance measure P. And we said it's learning if its performance at a task in T as measured by P improves experience. So there are several paradigms and three main ones in machine learning that you've heard a lot. So probably you already have this kind of presentation hundreds of times already, but just to make sure that we have the same definition. Supervised learning is the most common use case in machine learning. So it's when you are trying to estimate a function that will associate a set of label training example, x, y, y, I, and try to identify the function that associates x to y. So that's the most commonly used. The 101 on that example is trying to predict the price for housing in some kind of town, usually Boston, because of the data set on that, based on several features like neighborhood, size of the apartment, number of windows, and so on, trying to predict the price of a new apartment. So that's a classic example. Then the unsupervised learning, which is more hard to define formally. It's more commonly used for clustering. So that means trying to group unlabeled data. That's the difference with supervised learning. Data here is supposed to be unlabeled. And try to find groups of homogeneous classes. And then there's reinforcement learning, the third big one. So to quote a definition from Sutton and Bartow, which is the main reference book on the topic, it's about learning what to do, like we do as humans, basically. So how to map situations to action, and because we need a mathematical framework for that, the goal is to maximize a long-term reward. So trying to learn what it is best to do to in the long run, have the best reward. So what does that mean in detail? So hopefully it will be clearer, if not already familiar, by the end of today. And also, maybe. So deep learning also is a term that we use a lot. So this is a subset of machine learning methods that are based on neural networks and that you can find in all those three paradigms. And actually today, we are going to go through reinforcement learning in a bit more details and introduce one algorithm which is based on neural networks. So it's a deep learning algorithm. So reinforcement learning, just to, if you're not familiar with it, there's a lot of application areas and a lot of them you have heard about. So example is autonomous driving cars. So it can be used for optimizing the trajectory, dynamic paths, motion planning, but also recognition of patterns on the road, on the pictures that the camera are visualizing. It's used in robotics. For robotics, you have what is object grasping, being able to handle objects. Also navigation of the robots, and also coordinating simultaneous tasks. One hot topic is generative AI. So one of the use cases for reinforcement learning in generative AI is what is called reinforcement learning with human feedback, where you're trying to improve an existing model. So for example, ChatGPT is using a GPT model and is using reinforcement learning with human feedback. So they will collect some feedback from humans on various prompts and select the best one using reinforcement learning. And the same goes for Llama 2, the open source meta model. There's also a lot of application, and that's one of the examples we will use today to make it a bit more fun. In gaming, so a lot of papers were published on that, got a lot of attention, let's say 5-6 years ago. So it started with chess and pinball. Then there was Atari 2060, so that's one example we go through today, how to improve and beat the computer at the game. But also the main attention was when they started Google DeepMind, I think it was. No, it was OpenAI. Did the AlphaGo program to beat a human master at the game of Go. So that was a big breakthrough. Then there was AlphaCraft by Google DeepMind this time, so beating a master at StarCraft 2, and also in Dota 2. So that was a lot of press at the time. And it's also used, and that's mostly what we are going to talk about today in terms of use case, for cloud systems in general. So for scheduling jobs, congestion control, resource optimization, database optimization, and also the use case we're going to talk about today in more details is auto-scaling. Reinforcement learning, so let's dig a little deeper into that. So this is the most common figures that you can find on reinforcement learning coming from the same reference book I mentioned earlier from the Sutton and Bartow. So we'll try to build on that to explain how to map that to Telco core environment slowly. So in reinforcement learning, you have an environment that you can observe, that has a certain state, on which you can compute a reward. That's an aspect that we will have to explain a little bit more. And an external agent that will act on this environment, so doing actions. So you'll see some example of that. And this action will have an effect on the environment, which will be in a new state and with a reward. So we're going to walk you through that and some examples today. Some examples that you can find in the literature, pretty common. So this one of the 101 of gaming with reinforcement learning. It's from OpenAI gym environments, the cart pole. So where you have a cart that you can move from left to right along the axis, and a pole trying to stand on it without falling. So in this case, based on the figure we saw just before, the action space you can have, you have two different actions. The cart can go left or right. The observation space, so the state of the environment, will be based on the cart information. So it can be the position of the cart and the velocity of the cart, and also the pole, the current angle of the pole, or its velocity. And the kind of reward that you can have in this case is you want the pole to be standing up as long as possible. So the reward you could have is to have +1 every time basically the pole is not down. So that's a basic example. So if you want to try the hands-on part, just to make sure that you have everything ready, you can switch to the GitHub we have shared. And if you have not the URL, you can find it here. So it's github.com/jeffreys-isin. And on there, there's a small notebook that you can open with Google Colab. So I can walk you through that, but I don't see much laptop. So basically, if you want to do that, I see some laptops opening, so let's wait a little bit. Just a small example, and to check that everything is working on your side about how to have a small working example. So it's notebook, but it's probably will only work on Google Colab, because otherwise you need some administrative rights to install it and so on. So most of the code you see is about running the visualization inside the notebook, so it's not very useful, this first part. What is really interesting is here, importing the example. And for this first example, it's just importing the environment that we want to create, so the cart pool I was mentioning. And it's not doing anything smart for now. This example is just doing a random action. So it will just take one of the possible action, and at every step of the process, try a new action and observe what is happening. So this is not doing anything smart, but we will show you a smarter version later on. But just want to maybe introduce a couple of more terms that are common to understand in reinforcement learning. Is the notion of training process. So you have like a first notion will be the episode or epoch. So basically, if you look at a game, it will be a new game. So as long as you have not lost or won, this is a new episode. And during that episode, you will have a number of steps. So during one step, you will take one action. And this action will change something in the state. So in the case of the card pole, it will have it move along the axis. So I need to run it to show it. But and once you have won or lost, the current episode will be finished, and we will restart a new episode. So this notion that we will use sometimes of episode, so that's the game. As long as the game is running, we continue. And episode, the step, which is just one step, one action that will be taken. So if I run it, for the one of you who want to run it, it's pretty fast. You just run them clicking on the button, like it's a notebook. So it's not doing anything smart so far. So hopefully, if that works, you should see the picture appearing once it reaches this cell. And I should have started it earlier because it's still installing. Okay, so while it's running, I will just switch to the slides. So I will get back to it. Just want to introduce another example just to make sure that it's clear. So it's still not a telco core, but explaining how we use reinforcement learning in this case. Another gaming example is the Space Invaders, so one of the Atari games I mentioned before. So in this case, there's a bit more action you can do. You can move on the left, right still. You can also fire on the Space Invaders, so there's several buttons you can do. But also you can choose to do nothing. So that wasn't the case with the card pole example. And what is interesting here is that the observation space is very different. So what is mostly done for this kind of game is there's two strategies. Either you observe the memory, the content of the memory, and it's possible because on this old game, the memory usage was very limited. So it was a few bytes, kilobytes at most. So you can just observe the values in memory. Or you can observe the full screen, so pixel by pixel, and identifying what is happening. So that's what is mostly done in this kind of games. It's also possible because it's a small screen, so you can run it very easily. It's much complex to do with StarCraft and what DeepMind has done. But and in this case, the reward is basically just the points you're scoring on the game. So you have to train your model to learn how to read this screen and see if it has won or not. So hopefully it makes sense later on. So just go back to my notebook. So you can see when it's running, so it's a bit late now. So let me restart the last cell. So you can see that for now it's just doing random action, so it's moving. It's not falling because it's a very few steps, but it's not doing anything smart at this stage. Hopefully it will be smarter later.
So there is this branch of AI which is reinforcement learning. So reinforcement learning mainly is concerned with sequential tasks, you can say, like autonomous cars. When AI has to learn how to drive a car, it has to learn to take sequence of actions, and those sequence of action will help the agent to achieve some goal. So that's really different from predicting just a single data point or some trend of the weather. So here the problems comes with a notion of goal. And this diagram you can see is an intuitive explanation of how reinforcement learning works in general for any kind of problem. So the agent you see here is our learner. So agent is the one which learns the problem which you are trying to solve, and the environment from the examples, you can say it's the carpool environment, or for the autonomous car, the environment can be the roads or its surroundings. So agent at discrete time steps interact with the environment, and by interaction you can see when agent interacts with the environment, it collects the state. So state is nothing but just the current representation of the environment. So by observing the current state of the environment, agent selects some action, and after that action is executed, the agent receives a reward. So reward is nothing but just a feedback of the quality of the action, and as the result of the action executed, the environment transitions to a new state. So more formally, you can say reward is the immediate feedback that you receive as the result of action you executed. And there is one more term uh, which is called return. So as I mentioned, reinforcement learning is concerned with the sequence of action you take over time. So return is nothing but just the rewards, the sum of rewards over this complete sequence. So that's what we call return. So what agent learns? So agent learns the uh, agent learns how it can map the situations to actions. So it basically learns this what actions to take in which states. So more formally we call it policy. So agent learns the policy, and if some policy generates highest returns, we call it optimal policy. So the goal of the agent in general is to learn an optimal policy. Okay. And there are some more terms concerned with this agent and environment interaction. So before jumping on to these terms, I hope this agent interaction is clear to all of you. Okay. So we are going to go a little bit deeper into reinforcement learning, and so just to make the foundation, there are few terms. So one is value function. So value function is something which tells the agent the quality of a state. So how good it is for the agent to be in a state, it is represented by this value function. So value function is nothing but the expected return from some state. And similarly, there is a notion of Q function. So Q function is more concerned about the actions you take in some state. So the concept is same as the value function. It is also a expected return, but it is concerned with you took some action, and you follow a policy pi, and the return you got at the end is the quality function. So in general, it tells you what was the quality of action uh, in the state. And there is one more term called advantage function. So advantage functions just tell you that how much better it is to take one action over another. In general, it tells you how much extra reward you can expect by executing some action in a state. I hope these three terms are clear. I hope.
For me, the way you the value function and the Q value, I didn't quite get the difference from between the.
For value function, you can say. So reinforcement learning is concerned with following a trajectory. So starting from state S, you go until the end of an episode, and the uh, reward you accumulated until the end of episode is called value of that state. But this Q value depends on the action. So if you are standing at some state and you took an action over there, uh, so the return that we are going to generate after executing that action is called quality function. So the value function doesn't depends on any action in particular. It just says that any general action you can take, how much reward you, how much return we are going to expect. But this Q function is more concerned with the action, the particular action you are taking. Okay. So next we have the classification of algorithm. What are different algorithms are there? So based on how the agent can interact and move in the environment, it is classified into model based and model free. So model based algorithms are the one where agent knows that after taking some action in which state it is going to occur and what reward it is going to get. So all of the dynamics of the environment, all of the transition probabilities are known beforehand. So agent knows where it can move, how much reward it can expect. And on the other hand, we have model free. So in model free, the agent does not have any idea of the reward it is going to expect after taking certain action. So most of the real world problem falls into this category, and since agent doesn't know nothing where it is going to land next or what it is going to get, so the only way to learn is through experience, through trial and error. So model free is further divided into two parts. So as I mentioned earlier, the goal of the agent is to learn an optimal policy. So model free methods rely on this concept of learning policy. So there are these value based method which learns the value function first and then derives an optimal policy. So and the policy based are the one which learns the policy directly. So value based is further categorized into two parts. So one is of policy. In of policy, there are two policies that agent use. One is target policy and one is behavior policy. So using behavior policy, agent interacts with the environment, and uh, it eventually learns the target policy. So the target policy and behavior policy are two different things here. And other is on policy. In on policy, there is no concept of behavior policy. So agent uses same policy to explore the environment, and it learns the and it continually improves the same policy. So I hope that classification is clear. I guess the examples of on policy would be this state action reward and state action algorithm. And for the off policy, we have this Q learning, and Q learning forms the foundation of all. So Q learning forms the foundation of all, and the further classification like DQN, DDQN, and D3QN are the uh, deep reinforcement learning versions of this Q learning. So these three DQ and DDQN uses deep neural networks to over the concept of Q learning. And in this tutorial, we are going to focus more on this D3QN, which is also called as dueling deep Q networks. And for policy based, we have this deep deterministic policy gradient and proximal policy optimization and actor critic methods. So this is all the taxonomy part of algorithms.
Sorry, what was the difference between the value-based and policy-based? So value-based tries to learn the value function, and policy-based?
Value based first learns a value function. So value function which generates the maximum return, it becomes the optimal policy. So we are deriving the optimal policy indirectly. But in policy based, we took a policy, we act according to the policy, and we keep on improving the same policy.
So it doesn't use value functions or action value functions.
No,
The policy based.
not at all. So in further slides, we are going to form understanding over Q learning, as I mentioned earlier. So in order to understand the working of Q learning, we have to keep in mind few mathematical equations. So one of them is Bellman's equation. So it is nothing but a way to express Q function or value function in a recursive manner. So it says that value function can be written as the sum of immediate reward and discounted return from the next state. And similarly, Q function can also be written as the sum of immediate reward and discounted return from next state on executing action A and thereafter following policy pi. I hope that's clear, or further clarifications on this.
What is the value function does not depend on t, no? Or is
Actually, it does depends on t. It's just the way we wrote it here, but it depends on t. So value function at current step t is the sum of the reward that you got at the next state and the value function for the next state.
Okay, thank you.
And there is one method called temporal difference learning. So it is also one of the method to learn the value function, and it is based on the difference between successive value estimates. So I'm not going to deep dive into what TD learning is, but I'm just going to state this TD learning rule, which is going to be used in the Q learning part. So agent continually interacts with the environment in this case, and it improves or updates the value function using this formula. So you can say you can see that it is also a sum of the reward that you got, the immediate reward that you got, plus this value function from the next state, and you just subtract the value of the current state. So this whole term is called TD error. So you are taking the difference of the reward that you can, the return that you can expect from next state, and you are subtracting what was your current value estimate. So this is how you are going to update the value of current state, I guess. And this formulation also comes from the Bellman's equation. So you see how the TD target is related to the Bellman's equation we have mentioned. So just keep in mind these two terms, the TD target and TD error. I guess. Any clarifications? Okay. If not, so this is the first model-free and of policy-based method, which is aims to learn the Q function, and it extends from the temporal difference control algorithm, and it is a tabular learning method. So in a table, we store the state and action and its corresponding Q value. So as the agent interacts with the environment or explore its environment, it stores this state and action and Q value in a table, and so this table keeps on growing as agent keeps exploring its environment. So The way the table is updated, this formula comes from the temporal difference algorithm, and it can be stated that TD learning is nothing but I mean sorry. So it can be stated that Q learning is nothing but TD learning over Q function. So it's TD learning but for the Q function. So the way we exploit this table when the agent has done all of the exploration, the way we make use of this table is we start at some state, we select the action with maximum Q value, we transition to another state, and in that state we again select action with maximum Q value. So here this becomes our policy, the question you were asking earlier. So this becomes our policy to select action always with maximum Q value. So you were asking for example, so maybe when we were filling this table, we did not always choose the action with maximum Q value, we instead took a random action. So with some probability we took random action, but on the other times we relied on what was our value estimate to update this Q value.
The behavior policy is the one that explores the space and not
environment.
necessarily takes actions based on the maximum reward. And the
Yeah.
target policy, because here there are two policies, no? The
Yes,
behavior
behavior
policy
and target.
and the target policy. The target policy always chooses the action
With maximum Q value.
with maximum Q value.
Yes.
And the behavior policy
Sometimes chooses random action and sometimes chooses the action with maximum Q value.
Oh, I see. So the behavior policy is used to fill up the table,
Right.
and the target policy will use the table always choosing the action that maximizes
Right.
the Q value. Okay, okay.
So when we were exploring the environment, those value estimates were not that good. So it will eventually improve. So it's not the policy at that time was not deterministic. So do you see any problem with this learning method? I mean, what challenge it can have in the long term, this learning method?
The table can grow.
Exactly. So state, when your state is continuous, I mean when it's not discrete, the table can definitely grow larger and larger, and it will eventually becomes unfeasible to store this table, and again it will not scale well. So thanks to deep neural networks, they are good function approximators. So we replace our Q table with a deep neural network. So this deep neural network is used to predict the Q values. So you give input the state and predict the Q values, and eventually we in deep Q network we eventually have to improve this Q network as much that it can learns to output the good Q values. So again, deep neural networks works in a supervised learning way. So we have to provide it a target. So remember in the previous slide we talked about TD target. So it forms the TD target like this, and this deep neural networks learns by minimizing the loss between the predicted Q value and actual Q value. So Q predicted is nothing but the TD target, and Q actual are the current estimates of Q function. So this is it, and to formulate this problem, it uses two networks. So one is policy network, which actually generates the estimate of current Q values. So policy network outputs the current Q values, and target network is used to create the TD target in simple words. And TD target is keep fixed. sorry, the target network is keep fixed, and in certain episodes or certain time step, the policy network is copied into target network. If this working is clear. Yeah. So again, the DQN has this problem of moving target because we are having this two networks which are just copy of one another, and it's kind of becomes chasing your own tail, right? So it suffers from the overestimation bias and the moving targets problem, and there we use double DQN, and double DQN is different from DQN in a way that I mean it uses a different method for TD target formation. So just like DQN, it uses two networks, but the way it forms the TD target is like using policy network. It selects the best action to take in the current state. So I think in DQN we used policy network to output the Q values, but here uh, we use the policy network just to select the action, what could be the best action, and to generate the Q value we are using the target network here. So that is the difference which comes with double DQN, and this working is more formally written in the form of this Bellman's equation. And in this use case we used dueling DQN, and dueling DQN is the combination of DQN and double DQN. So D3QN is just introduced to improve the learning efficiency of Q function. So it is just a architectural enhancement, you can say, and it can learn which states are valuable without actually learning the effect of each action. So it does so by decomposing this Q function as the sum of value function and advantage function. So neural network is split into two streams, as you can see. So one stream estimates the value of a state, and the other stream learns the advantage function. And through a special aggregation layer, we combine these two to create our Q values. So this is how agent can learn how good it is for the agent to be in that state without actually thinking about actions.
Sorry, one question.
Yeah.
So in all these methods, in the end, the target policy will always choose will always use the Q function to
Yes.
select the action with the maximum value, right?
Yes.
These are just different ways of estimating that
Right.
Q function, right?
Right.
But we're not changing the way
Exactly.
the target policy will choose the action.
Exactly.
Is that
exactly.
okay? Now, can you this thing of the streams? Can you explain again this D3QN? How does it estimate the Q function? How does it uses these three? Is there three neural networks here?
No, it's just one neural network, and the last layer is split into two parts.
Okay.
So one stream is for V of value function, and another stream is for advantage. And then we introduce one aggregation layer which just takes the sum of these two streams.
Okay. Okay, I can look at it a little bit in more detail later.
Maybe just to add on this, we try to have a color code here. So the neural network is split in two.
Okay.
The first part is common to the two value stream and advantage stream. That's why it's orange color here. And the last, as Shantan was said, the last layer has a different shape. So one is computing the advantage depending on the action, and the other one just compute one value. And the Q function is
Because the
aggregation
Q
of both.
function is the difference between value and advantage. What was the equation for the Q function as a function of value and
Next
advantage?
slide. Here.
Is the sum.
Yeah.
Okay, so you
Most-
use one part to compute the advantage function, the other one to compute the value function, and then from that you get the Q function, no? Okay. Okay.
So that's about how the deep Q networks work, and to make it work, we used some further implementations. So one of them is prioritized experience replay. So the way that off policy learning algorithms work, it learns by it first collects the experience and it uses that collected experience to improve the neural networks. So experience replay buffer is nothing but it's just a data structure which stores the experience, which is typically a tuple of state, action, reward, and the next state. And data is sampled randomly or uniformly from this replay buffer. So one of the reason that we use experience replay buffer is to break this temporal correlation between the data points. So when you interact with the environment, data comes with a temporal correlation. So it has dependency of sequences. But as you may know that the optimization methods like deep neural network does not work well with the data which has temporal correlation. So it requires data to be in a normal distribution, I believe. So by sampling data randomly, we ensure that our data is independently and identically distributed. So based on this experience replay, there is a thing called which was introduced with the DQN. It is called prioritized experience replay. So the concept is same, but it differs in the way that it samples the data point. So it gives high priority to the samples which has the higher TD error. So by learning on the samples which has high TD error, the DQN is focusing more on the situations which are more challenging to it. So again, we are improving the learning efficiency or sample efficiency, and maybe we can improve the convergence of the algorithm. So, and further extension that we used action masking. So as the name suggests, action masking is nothing but it's just a way to hide the invalid actions from the agent. So it prevents the action to prevents the agent to not to take the wrong actions in some state. So for example, in a car driving use case, the agent should or the car should never drive towards the cliff. So that's the invalid action at every time. So we forbid the invalid action, and by using this methodology, we can improve the learning speed of the algorithm. So agent should not waste time on learning the wrong action. So again, it will keep on performing those wrong action, keep on receiving this negative feedback, and eventually after certain time steps it is going to learn that, oh no, I don't have to take this action. So instead of doing that long process, we use this action masking. That's about the algorithm. So we'll move more further into the use case part, which Guillaume will introduce. Thank you.
Thank you, Shantanu. So hopefully now you're all caught up on reinforcement learning and the discrete QN example. So you'll be able to play with it or watch how it works in more details in implementation during the hands-on part. So discrete QN is only one example of algorithm. That's the one we used in our work. We are also exploring others, but that's one example of algorithm you can use for the use case I'm going to introduce now. So we're going a bit back and forth between the reinforcement learning aspect but also the use case, because this is a network conference and that's what's important for us. So what can we do with what we just saw in network? So we focused on what we call the scalability problem. So the scalability problem we define as a scaling of cloud resources allocated to network function according to the workload to guarantee the quality of service. So, and specifically in the use case, I'm going to explain in more details the actual setup we had. We focused on the horizontal scaling. That means adding or removing the number of instances of a packet core, LTE packet core. And I'll explain why it's LTE, not 5G, but this is the same, basically, use case. So the objective here is to automatically scale the platform depending on the user traffic. So for example, if you have a LTE network described here, so this is a standard 3GPP LTE core where you have the core function, MME, S gateway, P gateway, and the radio access part connected to it, data network here, and of course the HSS for the subscriber database. So the scalability problem can arise when you scale your network, you add new inode B, so radio access network elements, antennas, and so on. And so you will need to scale your network. So maybe it's MME, maybe it's here, it's a S gateway that you need to scale for whatever reason. And if you keep growing your network, you will need to add further capacity for maybe a MME function or S gateway function. So the problem we're addressing is how to automate that. And specifically, we explore how to use reinforcement learning to do that. So for the auto-scaling part, just to give an overview of the solutions that exist. So it can be split in two techniques to address that, because as I just said, the goal is to autonomously and dynamically provision, but also deprovision a set of resources that it can adapt to the workload. Also a secondary objective, and that's always a challenge to have a secondary objective, is to optimize the overall cost, because one easy solution is to scale at most. So here you have plenty of resources, your quality of service is perfect, but the cost is too high. So the goal is to find the right trade-off between cost and SLA of the application. So there are two kinds of techniques. Well, there's a whole literature on that, but let's say the two main techniques, reactive and proactive. So the reactive part is when you have you scale your system in real time or near real time in response to the actual workload. So it can be threshold based or event based. So for example, and that's the baseline that we had in our paper, you could say that you add resources when your CPU usage or memory usage reach a certain threshold, like 80%, or you scale down your platform when the resource usage is lower, like under 20%, you decide, okay, I don't need that many resources, I can scale down, scale in. So this is good for smooth and gradual workloads. It's very straightforward to implement. It's just a binary threshold or event. And it can help save some cost and making sure that the platform is available. But the problem is that when you have a very fluctuating workload, and you might go very often just above or just below the thresholds. So in this case, you have what we call resource flapping. So you will add and remove resources. And especially if it takes a long time to provision resources, this can be a problem because it's not automatic. Just +1 can take time, as we will see. In the case of the network, it takes quite some time. So another category of solution is proactive. So when the system adjusts preemptively to account for the upcoming workload. So there are a lot of techniques that are currently explored for that, using, for example, control theory, queuing theory, machine learning, and, for example, time series are used for that, to forecast the workload, so to be able to scale ahead of that. But here we are exploring reinforcement learning, so to try to learn the scaling policy by trial and error. So we'll have these networks that will try to do some action, learn from this trial and error to see what is the best policy to achieve the objective. So the pro of this kind of approach is that scaling ahead of the demand ensure the availability and the QoS of the service. And it avoids the resource flapping issue because you predict the workload in the future. You try to predict the workload in the future. You don't take as many actions, and you don't take too many actions where there's just every time a threshold is breached, for example. The con is that it's very complex more complex to design, as you can see from the previous slide. This is not an obvious algorithm, and also this is prediction, so this is not sure. So it's always a challenge to have operational teams accept this kind of solution. So why do we use reinforcement learning, and why did we consider it was a good solution? So autoscaling is not a new problem. It's been here for quite some time, and it's a classic automation control problem. And it was abstracted as early at the beginning of the century with all the consideration about autonomous networks, and mapped to what was called the MAP, control loop, which repeats itself over time, where we have a system that monitor the system, the performance of the system at regular intervals, and analyze what, based on KPI, what needs to be done, plan the provisioning or deprovisioning of the platform, and execute those actions. And this is basically what we describe with reinforcement learning. So that's why it seems to be a good candidate to use reinforcement learning to address this kind of control problem. To give more details about the environment that we used, and I say environment because also that's a term that is used in reinforcement learning, so you will see how this makes sense, hopefully. So we used the open source virtual EPC Magma, which allows to simulate the LTE network. So this is a project that was started by Facebook originally, that is now part of the Linux Foundation, Magma. So it's 5G ready now, but it was not when we started our work. So that's why we use the LTE version. Doesn't change really the use case, you will see, because Magma has a very specific approach that combines the various network functions of the core in a single software they call the access gateway. So all the MME, S gateway, P gateway, and HSS function are just in one software. And one interesting aspect of it is that, and why we chose to start with that, is that it's really an industrial solution. So it's available for deployment by operators. And also it provides a lot of dashboards and metrics. So there's a network management system that is part of it, based on open source solutions that are very well known, like Grafana and Prometheus. So that made it suitable to collect information about the platform. So to give a bit more details on what we used, so that's not what we are going to use for the hands-on part because it's way too complex for a tutorial, but that's what we used, and that's what we will be using a simulator for the hands-on part. But the testbed itself was deployed as virtual machine in the cloud, so a cloud by a range flexible engine. And all the tests, so simulating the user equipment and radio access network, was done using scripts that are based on another project from the Magma project, which is S1 AP tester library, named after the S1 interface of the core network. So basically, in Magma, we have all these functions that I showed earlier that are part of a single software. So that means that when we are scaling, we have a simpler problem, let's say, with Magma compared to other solutions, is that we are scaling the full access gateway every time. So here, it's a way of simplifying the problem. Also, we scale all the network functions all at once by scaling the access gateway. We have also tested on other open source projects like Open5GS and Free5GC, but the focus on the papers that we had published and what we are going to show is based on this architecture, a bit simpler. Just a bit more details if you want to implement reinforcement learning on the telco core, because this is the goal of this tutorial. There's a lot of requirements, there's some requirements, and specific developments you might need to do. So what we've done basically, you need to be able to provide traffic to this platform. So here we had to develop a specific component, the workload generator on the left. So here it will create a workload based on information that we provide to him. So we use some actual information from the Orange network here. And it will send the load to the available instances. So in the case of this architecture based on Magma, an instance is actually a pair where we have a Magma access gateway on the right, which includes all the network function of the core, and the user equipment and radio access network that we are simulating. So this is based on S1AP tester. So I can give a lot of details on that, so basically consider that this is the software that is also provided with the Magma project. It's a one-to-one relationship. So when we scale the platform, we scale not only the core network, but also we need to scale the tester that will simulate the traffic on the Magma access gateway. So we have a simple script that we developed that is just the use case. So it just simulates, in this case, attaching and detaching new sessions on the core network. And we are not simulating the data plane, we are just simulating the control plane because it's much simpler in terms of deployment. And we didn't consider that the data plane will bring very new information for the process and the reinforcement learning aspect of it. So here, so basically the RL environment, to speak RL now, will be the Magma infrastructure and various instances. Also the Magma network management system that will provide the metrics, so the state of the environment. And we have an external agent that will observe that and we decide to take some actions. So when we scale, for example, when we scale out, so when we add instances, we will add a new pair and we will split the traffic, load balance the traffic. So if you want more details, I can give some, to all the available instances. And we will have the agent collecting the state and pushing some actions to the platform. I'm going to give some more details on that. Is there any question on so far?
Quick question. Why you say only control plane traffic?
For sake of simplicity, because it's much easier to implement just the control plane than the data plane. So that will mean like simulating a whole use case with some connection to data network. And also for what we want to explore, which is how to have reinforcement learn on this kind of environment, we didn't feel that it will bring very useful information. Just control plane is already bringing a lot of information for the scaling. But of course, it can be added.
But what does it mean? So I thought you're creating traffic with the workload generator. You're creating traffic. This simulates data plane like UE and run. These are data plane functions, no?
It could also generate some data plane traffic and function. But here, the workload basically just say how many devices, UEs, needs to be connected at a single moment. So the control plane is about the connectivity and so the session handling of the user equipment, but the user equipment don't send anything on the data plane.
I see. So will you generate these instances of UEs and access points, no? And G-node-based elements of those, and then you assume that it has to be some control plane traffic from the HS, no, from what? So which is the traffic essentially from the MME to the...
So to explain, so the workload generator it will just inform the tester how many UE equipment they will simulate at a given moment. So that means that it will initiate, for example, that many connections based on the input to the MME.
To the MME.
So, yeah, and the MME internally, because it is part of the access gateway, so we are not doing anything specific on our side, it will connect, it will read information from the HSS, set up everything with S gateway, P gateway. But we are not using this connection to do anything really in the use case.
Okay, and there is also no connection to the P gateway or S gateway from the testers. The testers only communicate with the MME.
Yeah, because that's the way it works in the network itself.
Okay.
But
I see.
Some things are happening in this gateway, P gateway, because it's establishing the sessions for the equipment. But that's the way the LTE connection works, right? The device connects to the radio access, so both parts are on the tester side, and they connect to the MME. So that's the entry point.
Okay.
But setting that up is a large aspect of the project. So I can give more details on the tester, but I will keep that for question if you want exactly to understand how it works. This is really the software from the Magma project. So basically, it's a Python script that is using some wrappers they provide, and deep down, it's a shared C function library. But okay, if you have questions, I'd be happy to answer. Otherwise, we can skip that part, I guess. For the metrics part, so this is very important with machine learning and reinforcement learning. We need to be able to read the state on the environment. So here, the metrics that we collect can come from several parts, several components of the system. So the most obvious one is the Magma metrics from the network management system I mentioned before. There are about 100 metrics available, a bit more. So that can be like system metrics, memory, CPU, things like that, but also more fine metrics like about user information, equipment information, aggregated user information. So more network level metrics. Also, we found, and that's very specific to Magma, but that could happen with any core network, that some of the metrics were not enough to bring all the information we needed for the training. So we added our own metrics. So that was possible in Magma because it's open source, but we didn't change anything in Magma. We just have an additional script that collects more information about what's going on in the access gateway. So more specifically, the memory usage of the various process, because as you just said, it's mostly the MME that is the entry point. So there was no metric in Magma saying the MME is consuming that much memory. That was just an aggregated memory usage. So we have a finer analysis and metric on the memory usage of each component, and that proved helpful for the training. Also, we can use the cloud API. So the cloud that is hosting all of this infrastructure has its own API and metrics. So we can use them, but I think in the end, we are not using it anymore, really. For example, the number of running instances, the information you can get from the cloud API. So if we go back again to reinforcement learning, what we just saw before and just what I introduced with the use case. So in our case, the environment is a test bed, the Magma test bed, with all I just described, the access gateway and the testers. The state of the reinforcement learning environment is computed from the metrics. So that's something that you adapt based on what kind of training you're doing, and the kind of actions, the possible actions that you can take at every step. So most of the time, it's nothing. You won't do anything because most of the time your platform will be good enough. But you can scale out or scale in. So that means in our case, with the Magma, that will be adding just one gateway, access gateway, or removing one access gateway. If you use another solution, that Magma, where we have the 3GPP functions split in various software, that means you could scale in, scale out different components. So that will be more actions. But for Magma, this is a more simple example. You can just scale in, out the access gateway. So there are some specifics to this problem compared to the traditional problems of reinforcement learning. And for example, compared to the video game we mentioned before, there's an action delay. So scaling out or scaling in is not something that happens right away. It takes time for provisioning and making available new instances. So that means that the result of the action you are taking is not, you have to wait a little bit. So it depends on the infrastructure you have, the way the software is behaving, but you can't see it real time. And in most of the games, when you go right or left, you know immediately what is the current state of the game. Here, you need to adapt to that. And there's also the observation delay, because, well, like most network or IT systems, the metrics you collect are not real time. You have metrics collected. So at best, here it was 15 seconds. So that means the information you have can be not completely the reality of what you're observing, the current state. What you're observing is not exactly the current state of the system. Also, because this is a software we are training on, so basically we are, if it starts to make sense for you, we have an environment on which we will perform action. And so we give in the next part after the break, we will try to reassemble everything in more details. But basically, you will try to scale in and out, but as part of the training process, until the model has learned and the policy starts to be good enough, basically you will take some random action or stupid actions, really. So what can happen is that your software can crash. So here it happened a lot. So it can happen because you have the load that is increasing, but it decided to not scale the platform or to scale in the platform, or it just decided to take no action, because when it's already overloaded. So it can crash. And this is something that will happen because during the training process, even if we use the action masking extension that Chantal has mentioned, we will try to avoid the most stupid action. So for example, scaling in when there's only one instance, of course, adding 0 doesn't make sense. And it's normal behavior for any software to crash if you push it beyond its limits. So it will manifest in very different ways. And that's one thing is to be able to identify that it's not working anymore. So you're able to reset the environment, as we will see, or that's the game over for a video game. So here, once it's crashed, okay, you need to resume your environment for the learning, because trying to understand why it crashes means you have to understand really the software, and that's not the goal of this. The goal is to try to learn how to scale it and not how to find all the cause for crashes. But we can take questions for this first part. It will be more hands-on after we finished trying to everything together.
Yeah. The all problem may be caused from virtual machine. So because at that time already we have a free 5G, open 5G running over container platform. So lots of problem maybe disappeared if you're using cluster platform.
Yeah, I understand your question. So actually we use virtual machines because Magma at the time was not ready for containers deployment. So some things change when you use containers. That's something we are exploring. There are open source solutions like Free5GC, Open5JS, which are container ready. So that changes a bit of things. For example, the action delay will be shorter because you don't have to provision the full VM every time. You can scale a container is faster than scaling a VM, of course. But the overall process for the learning remains the same. Just obviously the environment is a bit different. The delays are different. But something remains the same. If we look at and that's the goal of the tutorial, how to integrate a telco platform in reinforcement learning pipeline. It's a bit different, the behavior in the environment, but the overall integration remains kind of similar.